Alright, let's finish up section 1.7 with some more analyzing the graphs and using some vocabulary that I mentioned in the last video, right at the end of the last video. Here's a little bit more mathematical approach to it. It says, suppose that I is an interval contained within the domain of a function f. Alright, so you have some domain of a function f. I is just an interval within it. It might be the values from 3 to 4. It might be the values less than 5. It just kind of depends on the situation here. So we're going to say f is increasing on I if f of x sub 1 is less than f of x sub 2. This means for all or for every x sub 1 less than x sub 2 on I. Which means as I'm going from left to right, my y values are increasing. This is just a mathematical way of saying that. I said the same thing at the end of the last video. And then in this case, f is decreasing on I if f of x sub 1 is greater than f of x sub 2 for all x sub 1 less than x sub 2 on I. So again, as x is increasing, my y values are decreasing, so it's dropping down or falling from left to right. Here it's rising from left to right. And f is constant on an interval I if the x values are the same, or excuse me, the y values of the x values are the same. F of x sub 1 is equal to f of x sub 2 for any x sub 1 and x sub 2 in the interval I. Now, I know that sounds a little bit complicated, but it's what I want you to start to get used to, including the notation here, because again, you will see the same kind of notation in calculus. Now, we'll use interval notation here to indicate our intervals. It says use interval notation to write the intervals over which f is either increasing, b decreasing, c constant. So we're just looking at the graphs now. We don't have an actual rule here. We're just looking at the graph. And you can see, and you're looking for part A, increasing, where it's rising from left to right. And I see that it's rising from left to right here. This is negative 1, negative 2, negative 3. So it is rising from left to right. This is for part A here. And it goes downward forever and ever here in this case. So it's rising from negative infinity to negative 3. And we're going to write these as open intervals. You'll talk about open and closed intervals with increasing and decreasing in a little bit more detail in calculus. And then you can see it's also increasing here from negative 1 to a positive 2. You can see it's rising from left to right. So we're going to take the union symbol and also go from negative 1 to positive 2. So that's the answer for part A as far as increasing. For part B, where is it decreasing? Where is it falling from left to right? Well, that's over here for values greater than 2. So we would say 2 to infinity. And you can see I have a small interval here from negative 3 to negative 1 where it's supposed to be horizontal, and that's where it's constant. So this would be from negative 3 to negative 1. That's not an ordered pair, that's the interval, the open interval there. Now, you can kind of see that in my graph, I have a point that's kind of like at the top of the hill here, and since my graph goes downward and downward here, we sometimes refer to this as an absolute maximum because the y value is greater than any other y value on the graph. But sometimes we have absolute and sometimes we have relative. Now, as it turns out, relative is more of a catch-all. It includes absolute. We're going to talk about relative extreme values. Extreme values meaning the maximums and the minimums. Sometimes we call the plural here, we drop typically like a um and we put an a, it's kind of a Latin deal. So we'll talk about extrema and relative maxima, that being singular, maxima being plural or maximums, relative minima, singular, minima for plural or minimums here. So I have perhaps a better looking sketch here where I have a curve, y equals f of x, and you can see my graph is going to continue going upward and downward. So these are not going to be absolute mins and maxes. These are going to be more specifically relative or local extreme values. And I have them indicated here at the top of the hill and at the bottom of the valley. F of a, that's the y value, is a relative maximum or maximum value since f of a is greater than f of x for all x near a. So it's kind of like in the neighborhood. It's in the neighborhood around point A here. And this is kind of top dog. Now it's not top dog over here because this is going to continue upwards. So somewhere out here, the y values are going to be greater than. But for right in here, and I just made a small neighborhood here, that is kind of your area that you look at, and you can see that at this point the y value is taller than no other. I can kind of liken it to this. In 6th grade, at my school, we had 5 6th grade classes. And in my class, believe it or not, I was the fastest kid in my class. I don't know, Carol Barron's might have been faster. She was pretty fast, but I was the fastest kid in my class. But I was not the fastest kid in 6th grade. In Mrs. Stone's class, Greg Hake was in that class, and he was probably the fastest kid. At least I think he was the fastest kid in 6th grade. So I was a relative extrema, or a relative maximum, because in Mrs. Tarn's class, I was kind of top dog here. Just like right around here at point A, f of a is the largest value. Terrible analogy, but I can't think of one better right off the top of my head. So, f of a is a relative maximum since f of a is greater than f of x for all x near a. F of b, way over there at the bottom of the valley, is a relative minimum or minimum value since f of b is less than f of x for all x near b. And that's, again, I try to draw like a little neighborhood of values around there. Okay? Now, when we talk about those points, we talk about the a being the location, in this case the x value being the location of where my relative maximum is, or perhaps a relative minimum, and then my y value being the what we call the value or the maximum or minimum value. In this case, the relative maximum, so it would be a maximum value there. And most times books will let you write the ordered pair. But if they ask for a location or if they ask for the specific value, then you give the x or the y depending on what's asked for. So I have an example over here. It says for the graph shown there, y equals f of x, determine the location and the value of the relative maximum. Well, that was right here. And you can see that this is negative 2, 2. So the location would be at negative 2, the value. So I could write, maybe I'll put it over here since I have a little more space. At x equal negative 2, we have a relative maximum value of 2. And then determine the location and the value of any relative minima, again, that's plural. I only have the 1 here, and that happens at when x is 1, so this is 1, negative 1. So I can write down something like at x equal 1, I have a relative minimum value of negative 1. Now, we're basing this just on a graph, and you could use a graphing calculator or Desmos to help you because they have the trace and they can give you a better idea. But when we get to calculus and we discuss the idea of the derivative, we'll be able to do this without a graph. We'll be able to do this straight from the rule of the function. But that's for another day.